Today I want to look at a particular application of refraction called curved lenses. There's two types of curved lenses. We have two names for each of those types. We have converging lenses, which are also called convex lenses. They're lenses that are thicker in the middle than they are at the edges. The other kind of lenses is called a diverging lens or a concave lens, which are thinner in the middle than they are at the edges. Now, there's two names for each of these, but I prefer the converging and diverging because it describes better the behavior of the lenses. You may see the terms convex and concave, but what I'm going to ask you to do when you see a question where it says a convex lens or a concave lens is translate it. Translate it from convex to converging, translate it from concave to diverging, because as I say, converging and diverging describe the behavior of the lenses better. You can see a couple pictures here that illustrate where we might use a converging lens or a diverging lens. The first one is actually a water droplet in space. That's a perfectly spherical water droplet because there's no gravity acting on it to make it a teardrop shape, right? When we look through that perfectly spherical water droplet at Chris Hadfield in behind it, you can actually see that the image of his face in behind that is, can you see that from where you guys are? It's smaller, clearly. You can see almost his entire face within that water droplet, and it's upside down, yeah. When we have a converging lens, which this water droplet acts as, sometimes we get an upside down, smaller image. Sometimes we don't. Sometimes we get a bigger right side up image. It depends upon where the lens is placed relative to the object, which in this case is Chris Hadfield's face. Now the second one that I have here is a diverging lens. You don't see a lot of applications for diverging lenses, certainly a lot less applications than we have for converging lenses. One of the most common ones is eyeglasses. Okay, I have diverging lenses in front of my eyes right now because I am myopic. I cannot see far away. I can see close up. I can't see far away. The reason that happens is because the rays of light coming through the convex lens in my eye converge in front of my retina. I need to spread those rays out to converge a little bit further back on my retina. So in order to make that happen, I have to use a diverging lens, a lens that spreads rays out. Does that make sense? Now, converging lenses are also used in eyeglasses as well, but they're used when you're hyperopic, which means that you can't see nearby. In other words, when you need reading glasses. Reading glasses are converging lenses, and then glasses that help, tends to be younger people, see far off objects would be diverging lenses. All right? What I want to do right now is focus on the converging lens, label a few parts of a converging lens and the diagrams that we're going to draw for converging lenses, and then start drawing those diagrams to predict what the images will look like. You saw a second ago, okay, again in the first diagram here, the Chris Hadfield behind the water droplet appeared to be smaller and upside down. How do we predict that he should be smaller and upside down in this photo? Or when is it that he's going to look larger and right side up? So this is a converging lens. It's called a converging lens because rays of light that go through this lens that are parallel to each other will converge. Rays of light that are parallel to each other will converge. They will converge at a point that we call the focal point. The focal point for this converging lens is right here. We're going to label the focal point F. Now, this dot over here, we're going to label 2F. That doesn't really have any optical significance in terms of rays of light going through it. It just kind of acts as a spacer for us when we go to draw our ray diagrams in a few minutes. F is the important part. That's where rays that are parallel converge. But 2F is twice the focal length, or in other words, twice the distance from the center of the lens to the focal length. Now over here on the left-hand side, I'm going to put these ones in quotation marks, F and 2F. the focal length and twice the focal length don't even really appear on the other side. We're just, again, going to use those as spacers. So I'm going to label them so that you recognize that this spot right here is the same distance from the lens as this spot right here. And this spot is the same as this spot. Now, a couple other things that I want to label. This spot right here, smack in the geometric center of the lens, is what we call the optical center. We're going to sometimes label that just as OC, the optical center. This line right here, this imaginary line that we draw perpendicular to the lens and smack right through the middle of the lens, we're going to call the principal axis. Although we'll often label it PA. All right, we have enough information now to start drawing ray diagrams for these lenses, which is going to enable us to predict what images will look like. Here's the first ray diagram. We have a converging lens here where our object, which is represented by this arrow, that object that's represented by that arrow could be a car, it could be a person, it could be a house, it could be a candle. You're going to use a candle for the object in a lab that you're going to do early next week. It could be anything, any object. We're going to represent the top of the object by the top of the arrow. So we know which way it's facing, right side up in this case, or upside down in another case. Once again, remember that this is going to be F, this is going to be 2F, this is kind of F, and this is kind of 2F, again, as spacers. We're going to say this time our object distance, which is the distance from the object to the optical center, our object distance here is greater than 2F. Now, it doesn't matter exactly how much greater than 2F, because the image is going to look pretty much the same no matter where I put the object, as long as it's put at a distance that's bigger than 2F. If I put it smaller than 2F, the image is going to look different. But anywhere out there beyond 2F, it's going to look the same. There are two rays of light that I'm going to draw off of this object in order to predict what the image is going to look like. There are millions of rays of light that are reflecting off of this object. There are two that I'm going to pick to draw. I'm going to pick those particular two because I can predict very easily where these rays of light are going to go. I'm going to draw the first one as if it reflects off of the top of the object and goes parallel to the principal axis. Okay, the reality is there's a million rays of light that reflect off of the top of the object. But there's one of them that reflects off of the top of the object and then goes parallel to the principal axis. I'm going to pick that one to draw here because I know exactly what's going to happen to it. It's going to refract or bend as it goes through the lens and go down straight through the focal point. Parallel rays refract through the focal point. Now, the reality is, you understand here that I've done a little bit of a simplification. Okay, when this ray of light goes and hits the lens from the air, it bends. And then when it goes from the lens back to the air, it bends again. So there's actually two refractions taking place there, not one. But I draw it as if it's just one refraction taking place because it's easier and it gets me the exact same results. So if we can do it in an easier way and still get the correct result, let's do that. Just understand that that's not actually the way it would look. It's bending twice rather than just the once. So first ray is always going to go from the top of the object parallel to the principal axis. The second ray that I'm going to draw is always going to be from the top of the object down through the optical center. Now, where's that going to go? It actually ends up going straight through the optical center. So you should get two rays that look like this. There are millions of rays. There are two that I've drawn. That's enough to predict what the image of this object is going to look like. Now it's time to actually label where the image is. If these rays of light started at the top of the object, the car, the person, the house, whatever it is that we were projecting with this lens, then they're going to intersect on the other side at the top of the image. So I'm going to say if the top of the object is right here, the top of the image is right here. The bottom of the object was on the principal axis. The bottom of the image is also on the principal axis. So in other words, my image is going to look like this. What are the characteristics, or sometimes we call them the attributes, the characteristics or the attributes of this image? Well, there's three. The first one is based on size. Is the image, okay, look at the image right here. Is the image larger, or is it smaller, or is it the same size as the object? It's smaller. This image is smaller than the object. If you can't see that, take a ruler and measure it. The image is smaller than the object. The second characteristic or attribute relates to its orientation, whether it's right side up or upside down. My object is right side up, right? The arrow is at the top. My image is going to be upside down because the arrow is at the bottom. So we're going to say that that's inverted. Or you could say it's upside down, whatever. Now the third one is the trickier one. The third one is based on the image and whether it can be projected or not. The third one, we're going to say it's either real or virtual. And in this case, it's a real image. That means that it can be projected onto a screen. When you look into the mirror in the morning in the bathroom, you're not projecting the image of yourself onto a screen. You're looking into the mirror in order to see it. That's a virtual image. If you go to a movie theater and project the image of the movie onto the screen, that's a real image. If we can project it onto a screen, it's a real image. If we can't project it onto a screen, if we have to look into the lens or mirror to see it, that's a virtual image. Does that make sense? Now, how do we know that this is a real image? We know that it's a real image because we have solid lines intersecting. You're going to see in a little bit, another few diagrams down the road, sometime when we don't have solid lines intersecting and produces a virtual image, but we'll deal with that when we get to it. So this image you can see is smaller, it's inverted, and it's real. That doesn't mean that we are projecting this necessarily onto a screen. We can look into the lens to see it, but it means that we can project it onto a screen. If we put a screen at this spot right here, any kind of screen like a movie theater screen or even just a piece of paper, we could project the image onto that screen. Now, our second diagram, we're going to move the object a little closer to the lens. You can see in our second diagram that our object is placed at 2F. This is still F, this is still 2F, and this is still 2F, kind of, on the other side. Let's draw those rays again. Where's that first ray go? That first ray of the millions that we're choosing to draw here, where does that first one go? We're going to reflect it off of the top of the object parallel to the principal axis. And then where does it go from there? It's parallel to the principal axis. It's going to go down through the focal point every single time. Second ray, where is it going to go? Down through the optical center again. Where's the image formed this time? Well, the top of the object was where the lines started. The top of the image is where the lines come together. The bottom of the image is at the principal axis. So my image is going to look like this. Let's take a look at my three attributes here. Is this image larger, smaller, or same size? How does the image compare to the object in size? Is it bigger than the object? Is it smaller than the object? Or is it the same size as the object, Kai? Same size. Now, is the image right side up, or is it upside down? The object is right side up here, right? Like the arrow is pointing upwards. The image is upside down. The arrow is pointing downwards. So we're going to say that's inverted. Listen, if you use the term inverted, that's great. If you just say upside down, that's fine. Okay, I don't really care what you say as long as you recognize what it looks like, that it's upside down. Now, there's that third one, that tough one again, real or virtual. Remember, a real image can be projected onto a screen, like literally the image you're seeing right now being projected from this LCD projector on the ceiling to the screen on the wall. Or like the image projected at a movie theater. That's a real image, can be projected onto a screen. Can this one be projected onto a screen? Yes, it can. It's a real image, therefore. We know that because solid lines are intersecting. Right now, that doesn't make a whole lot of sense to you because you haven't seen one where we don't have solid lines, but it'll make sense in just a few minutes when we deal with one that doesn't. Next one, we're going to move our object a little bit closer to the lens again. This time, if our object right here was at 2f, this time our object distance is going to be bigger than f, but smaller than 2f. It's in between f and 2f. We have the same object, car, person, candle, whatever it is. First ray is going to reflect off of the top of the object and then go parallel to the principal axis and then go down through the focal point. The second ray is going to go from the top of the object down through the optical center. And as it goes through the optical center, it's going to keep going straight through. Remember, there's actually a couple refractions taking place, but the net effect is what we have drawn on the diagram here. Where's the image formed? Well, it's going to be from the top of the object down to where these rays intersect. What are my three characteristics or attributes of this image? Is this image that's labeled over here, is this image compared to the object larger? Is it smaller? Or is it the same size as the object? What is it? It's larger, yeah. If you can't see that from your perspective or whatever, use a ruler and measure it. It is larger. Is the image, the red image that I have drawn here, is it right side up or upside down? If the lines intersect below the principal axis, it's going to be upside down every time. We're going to call that inverted. But again, if this is a quiz or a test and you say it's upside down or use some other term that describes the same thing, that's fine. As long as you know what it is, it doesn't matter what you call it. Now remember that third one, the tricky one, real or virtual? Real means it can be projected onto a screen. Virtual, it can't be projected onto a screen. What is this? It's real. Yeah, it's real. It's real because solid lines intersect. Shortly, you're going to see a situation where that's not the case, but for now, it's still real. So those first three scenarios, we get real images, images that don't have to be projected onto a screen. You could look through the lens in order to see them, but can be projected onto a screen. Where do you see something like this in real life? We've got an object that's placed at a certain point, and you project it onto a screen, upside down, and bigger. You're looking at it literally in the face. Okay, we have a projector right here that has a small object inside. There's this little LCD panel inside that's really, really small. And we project it onto a screen and make it bigger. But wait a sec, the image that you're looking at on the board right now is right side up, right? Have a look at the projector. The projector is upside down. So if we have a right side up object, it produces an upside down image in that situation. If we have a upside down object, it would produce a right side up image. Does that make sense? You're literally staring at the image of the object inside that projector in two ways, like the literal image on the board and then the ray diagram of what's happening with that on the board. Okay, this next one's kind of wacky. This time we're going to say that our object distance is at F, is at the focal length or the focal point. We got our same two rays as we always do. The first ray reflects off of the top of the object, parallel to the principal axis, and then down through the focal point on this side. The second one goes down from the top of the object through the optical center, and it keeps going through the optical center. Where do those rays converge over here? They don't. Right, they don't. We're going to actually try extending them backwards to see if they can converge back here. But the reality is, because they're parallel lines, they're not going to converge anywhere, right? Notice what I just drew, by the way. Those extensions of those lines are dotted lines. They're not intersecting. Those dotted lines aren't intersecting yet. But we now have something other than solid lines. You start seeing maybe where a virtual image could come from. What are the characteristics of this image? We don't have any characteristics because there is no image formed. Literally, no image formed. That doesn't mean light doesn't go through there. If you look through the lens when the object is placed at the focal length, you will see light going through, but you're not going to see a focused image. You're just going to see light going through the lens. Okay, if you're the object and you're standing at exactly the focal length of the lens, and I look through that lens, I'll see light coming from you, but I'm just not going to see you. I'm just going to see light reflecting off of you. Let's take a look at that last one. This time we're going to say DO is less than F. In other words, our object distance is pretty close to the lens itself, inside the focal length of the lens. That first ray is going to go from the top of the object parallel, as they all do, then down through the focal point. The second one is going to go from the top of the object down through the optical center. Keeps going straight through. Do they intersect on the right-hand side here? Nope. So what are we going to do with this? Let's extend them back as dotted lines. Extend the refracted rays back as dotted lines like this. Hey, look at that. They intersect over here. There's my image where the lines intersect. But it's not solid lines intersecting. It's these dotted lines, these extensions of these rays that are intersecting. What are the characteristics of this image? Is it larger than the object is? Is it smaller than the object? Or is it the same size as the object? What is it? Here's my object. Here's my image. Is this image bigger than the object? Is it smaller than the object? Or is it the same size as the object? It's a lot bigger, right? This image is a lot bigger than the object. Call it larger, call it bigger, whatever. Is it right side up or upside down? Well, assuming the object is right side up, then the image is right side up. I'll call that upright, but again, I don't really care what term you use for that, as long as it means the same thing as right side up. Now, is it real or virtual? This is an image that cannot be projected onto a screen. In order to see this image, you would have to stand over here and look through the lens in order to see it. When you do look through the lens, you would see it. But it can't be projected onto a screen. How do we know that? Because it's not solid lines that intersect, rather it's dotted lines that are intersecting. We're going to say this is a virtual image. It's a magnifying glass, right? Same lens as we had in the projector right there, but we place the object closer. When you look at, say, really, really fine print under a magnifying glass, where do you put the magnifying glass? Really close to the fine print, right? In other words, you put the object really close to the lens. You put the object inside the focal length of the lens. And what kind of image does that produce? When you look in a magnifying glass, the image is bigger, and it's virtual. You look in the lens in order to see it. It's exactly the same lens. It just depends upon where you place the object, what image you end up getting. All right, those are my convex lenses or my converging lenses. My other kind of lens is called a diverging lens or concave. A diverging lens is named a diverging lens because rays of light that are parallel to the principal axis will diverge, not converge, but diverge. Those rays that are parallel to the principal axis will diverge away from a particular spot that we call the focal point. This is going to be F. This is going to be 2F. This is going to be the optical center. And this is going to be, once again, my principal axis. The good thing about these diverging lenses, although you don't see them used in practical applications nearly as much as you do converging lenses, the nice thing about these is the ray diagrams all end up being the same. If we can draw one, we can draw them all. The first one is going to be drawn when DO is bigger than 2F. Remember, this is F, this is 2F. The first ray of light is going to go from the top of the object, parallel to the principal axis. Where does it bend? Where does it refract when it goes through that lens? How many people think it refracts down here? I don't even have a focal point drawn on this side this time. Goes down here. No, that would be a mirror reflecting, right? Not refracting. It actually refracts or diverges. That's why it's called a diverging lens, right? It diverges as if it's going away from the focal point. So if you draw a straight line from the focal point to where the ray is going into the lens, then that's the direction that this ray will go. Second ray, this one's easy, same as it was in the last set of diagrams. Goes right down through the optical center, keeps going. Where do the rays converge this time? Right here. Now, what would the characteristics of this image be, or the attributes of this image be? Number one, is this image that we see right here, is it larger, smaller, or is it the same size as the object that we started with? Smaller. And you know what? The next four diagrams, exactly the same. It's going to be smaller. We have an image that is smaller. Remember that. Every time you have a diverging lens, every time it produces a smaller image. What about right side up or upside down? It's right side up. It's upright. Remember that. Every single time you have a diverging lens, you have an upright image. Smaller, upright, every time. Is it real or virtual? It's kind of tricky because it looks like we have a solid line and a dotted line intersecting, right? Reality is we don't. We have two dotted lines intersecting. If we look at this second ray that went through the optical center, and we extend it back, then you can see you have two dotted lines intersecting, which means we actually have a virtual image. Cannot be projected onto a screen. Remember that. Every time you have a diverging lens, you will have a virtual image. In other words, all my ray diagrams are going to look the same. The next four ray diagrams are going to produce an image that is smaller, an image that is upright, and an image that is virtual. I would like you at your desks right now to try drawing the next 4 ray diagrams. Using the same rules as we've used for this one, knowing what the result should be. The image might move a little bit, the image might get a little bit bigger, a little bit smaller, but it's always going to be smaller than the object, it's always going to be upright, and it's always going to be virtual. Now that you've had a chance to draw the rest of the ray diagrams, let's just real quickly go through those just to make sure that you've got them right here. This time our object is at 2F. Our rays are going to look exactly the same. Our object is going to look pretty much the same. First ray parallel to the principal axis. It goes up away from the focal point. If we extend that, it looks like this. Second ray is going to go down through the optical center. We can see our image is formed right here, same as it was pretty much the last time. We have an image that is larger. We have an image that is upright. And we have dotted lines that intersect, so we have an image that is virtual. We cannot project it onto a screen. We have to look through the lens physically in order to see it. We stand over here. We look through the lens. We see the image of this object right here. Smaller, right side up, and virtual. Correct. It is large, smaller, you're right, rather than larger. In the bizarro world, it's larger, but in our world, it's smaller. Next one. Same thing, right? We have our object that is placed in between F and 2F this time. First ray is going to go parallel to the principal axis. It's going to go up away from the focal point. Let's extend that back through the focal point. Second ray is going to go down through the optical center here. And we're going to produce an image that is, I'm not going to write it down this time so I don't make a mistake. It's smaller, it's upright, and it's virtual. Same as it was the last 2 ray diagrams. Next one. We have our object that's placed at the focal point. First ray is going to go parallel and then up away from the focal point. Let's extend that back. Second ray is going to go down through the optical center and straight through. And again, you can see your image form. It's a little bit different size than the other diagrams, right? But it's still smaller than the object. It's still upright, and it's still virtual. And then finally, that last one, where we place our object really close to the lens. First ray is parallel and then up from the focal point. Let's extend that back. Second ray is going to go down through the optical center. It's going to go down like this. Our image is quite a bit bigger than it was before, right? But it's still smaller than the object, and it's still upright, and it's still virtual, meaning that if you wanted to see this image, you have to physically stand over here, look through the lens, and see it right there. It looks a little bit closer than the object really is. Okay, we saw that with a fish the other day, right, where we can have an image somewhere other than where the object really is. We perceive it somewhere else. And it looks smaller. We don't see the actual size of the object. We see the smaller image. And we see it closer, we see it smaller, we see it upright, and we have to look in the lens to see it, virtual.